this course, but all those first four will need. FAA says that they ought to be calibrated. The calibration should be traceable to what used to be called the National Bureau of Standards. Does anybody know what they call themselves these days? They've changed their name, I know that, but essentially they're the folks who say a pound is, this much, and so forth. Zero check. It's a good idea to check and make sure that your instrument, whatever it is, come back to zero. Now, one of the things we found in this course, the airspeed indicators may not go all the way to zero. Okay, they may stop at 20 knots or something like that. That's okay. If you're in a helicopter, you want it to go to zero. Instruments ought to be calibrated every 6 months, and critical instruments are for critical tests, really, every 60 days. One should have a configuration log that tells you what you tested and what the loadings were. Particularly in a development program, what you're going to find is that the airplane configuration is going to change. If you're dealing with a military program where they're putting bombs or various rockets or various things on the airplane, you need to know what was on there. So you have to have what we call configuration control, and the way I've generally done that over the years is make myself a logbook that for each flight I put what the configuration was, what the loading was, and correlate these two with a loading log, and for, say, loading number 3, configuration was number 6 or whatever, and number them, just so you can keep track. Because what will happen in a flight test is this. You'll be busy doing things. You'll be collecting data. When the weather's good, you're going to fly. Okay? And then when the weather's bad, you're going to reduce data. Trouble is, if you haven't identified that data with what the configuration and loading was, when you get ready to reduce it, you won't remember. I'll guarantee you won't remember. And then, oops. It's a big oops, by the way. That's the kind of oops that'll get you fired. So, it's important to keep these things in mind. Why do we want to do that? Well, we want to know what we tested and know what that data is that we've got stacked up on our desk. And the other thing is safety. Now, you may not think too much about this, but today, some of our guys here have worked for over the summer, have worked for companies that what the configuration is a software configuration. Anybody ever seen any software once it's loaded? I haven't. You can't tell what it is, can you? That computer will probably work. It'll probably give you something. But it may not be what you want. Or if it is what you want, do you know which software load it's tied to? In today's world, that's getting to be bigger and bigger. The F-35 fighter, one of the big problems they've had with it is the software loads. And all you need is some little guy coming up and say, well, it was just one line of code. made everything work completely different. So, from the safety standpoint, you want to be very careful with that sort of thing because it can kill you. Okay, weight balance, I'm not going to spend a lot of time on it, on all of these things. Things that are important to us on this: maximum takeoff weight or standard weight, and its abbreviation is W sub S. That's what we're going to correct everything to. For the Piper Cherokee 6, it's 3,400 pounds. That's the standard weight, okay? W sub S for the Cherokee 6 is 3,400 pounds. We're going to give you handouts that'll tell you what the empty weight is so you can calculate your weight amount. We're not too concerned about the minimum weight at this stage. Fuel weight, yeah, we want to know what and by the way, the fuel weight, we're using avgas, and aviation gasoline weighs 6 pounds per gallon. Okay, you may want to write that down. Avgas weighs 6 pounds per gallon, and that's what we're going to be using in the course. Test weight is the weight where we collected data that, at that time that we collected the data. That's the test weight, W sub T. Center of gravity, we're going to calculate that and before we go fly, and that'll be a fixed thing when we go fly. Center of gravity range or envelope, Cherokee 6 envelope looks something like this, and you'll learn that I'm horrible making freehand drawings on the blackboard, but I'll do the best I can. It'll look something like this, where this is weight, and this is CG. And we're going to be concerned with this point right here most of the time. That's the most forward center of gravity at maximum gross weight, okay? That's where that point is. Now we have some other, more forward center of gravities, but they're at reduced weights. So we're going to be concerned about this one. We're going to try to load to it most of the time, or at least close to it, okay? The other thing we like, a moment, again, is just a weight at some distance from the datum. And on airplanes, you will find that the datums are all over the place. Every company uses a different datum. If you've got a Cherokee, you'll find that it's someplace generally out in front of the airplane is the datum. If you've got a Cessna, you'll find that it's usually the firewall. If you've got a Beech, maybe the leading edge of the wing. Now, I happen to like the way Piper does it, puts it way out here because all the measurements are positive. Cessna's put it on the firewall, you've got positive and negative moments. Okay? But I happen to like the way Piper does it, so everything is positive. The other thing we like to deal with in flight test is the mean aerodynamic chord. Okay, now probably most of your courses you have talked about maybe the mean aerodynamic chord. Well, we like to use it in flight test because I know, for instance, that for a conventional tail airplane, the center of gravity travel will probably be someplace between 10% and 30% of the mean aerodynamic chord. Inches after datum, since the datums on these airplanes are all in different places, it doesn't have much meaning if I'm trying to compare airplanes, does it? However, mean aerodynamic core does, and I can compare a Cessna to a Piper to a whatever. Well, some of these other weights are not terribly important here. Datum and arm. Datum we talked about. Arm is the distance from wherever the weight is from the datum. This is a regulation that talks about how you determine the empty weight. Notice that it has to be determined with fixed ballast, any unusable fuel. And of course, that's a flight test. So when you first start, you're not going to know for sure you're going to have to measure the empty weight when you first start this thing without knowing what the unusable fuel is, because you're going to determine that from the flight test. Okay. Full operating fluids except water, and that means primarily oil, I guess. I'm not sure why they leave water out. It says the conditions must be well defined and easily repeatable. That's right out of FAR 2329. Well, we have several different envelopes. The designer's going to come up with a structural envelope, and that's the people who, the airframe group, as they're sometimes called, who does the design. They come up with the structural envelope. The structural envelope generally will be, if this is our CG envelope for flight test, the structural envelope may be bigger than that. Okay? That means that it's been static tested to this larger envelope. Generally, when we get into the flight test, we find that we can't achieve that envelope without making changes. So we will come up with the flight test CG envelope, which would be this one for the Cherokee 6. That's our responsibility as flight testers to determine what that envelope is, and that's the one that goes in the handbook, and that's the one that everybody flies to. Why did they test it bigger? Well, for growth. They may come back later and stretch the airplane or do something else, and having those static tests done just facilitates that. Yes, sir?
Wasn't that Beech 1900 based on a 300 here? And they did all these fixings to it too?
Yeah, they're all the same.
All the same.
King Airs, they just add sections, I was at Beech, King Air 100 was my airplane, so to speak, when I was at Beech. And that was, it was a stretch in the fuselage. In fact, we got into the flight test and we found that the original tail design didn't work.
Oh, that's
So they drilled out all the rivets and took that tail off and took a Model 99 tail, stuck it on, and rebucked all the rivets, and
So it has strakes and the...
Oh, the strakes and the other stuff are all flight test fixes. Oh, I can take you to the airport, and we'll do this sometime, and show you all the flight test fixes.
So this is after the fact?
Yeah. Didn't look like that when it first started. Until it got into the flight test. Okay. Some tolerances for weight and center of gravity. For flight test purposes, they allow us, not in this course, by the way, but in a flight test, like I went out and flew last week in this Thrush Ag plane, the W sub S for that airplane is 10,500 pounds. My takeoff weight was 10,921 pounds, okay? So they allowed me to overload the airplane for the flight test. The reason is, notice that they don't allow you to underload it, so to speak. 1% isn't very much. That's for performance testing. They want to make sure that you're correcting down rather than correcting up, okay? For other testing, notice that they allow you to go to minus 10%. So for handling qualities, you know, they would have allowed me to go to probably whatever 10% of that is, roughly 1,500 pounds almost, okay?
So what do you take?
I generally just, you know, whatever works on those airplanes, because you've only got one way of loading them, and that's putting water in the hopper.
Yeah, that's my question. What do you take? 1,500 pounds of equipment or
Yeah,
structure?
yeah, no, you just, like I say, you just take off some water,
Oh.
you dump a little water. And by the way, on that, you never land, you can't land with the full load. And it's pretty hard to dump the hopper. It's just a lever that dumps it, and it's pretty hard to dump it and get it stopped anywhere. You know, it'll generally go all the way, jerk the lever out of your hand when 500 gallons of water tries to come out that hole. But anyway, CG, notice that they allow 7% of total travel. That's quite a bit, because the total travel is from here to here. It's not the total travel at that weight. Okay, it's this total travel, so plus or minus 7%, you can see that would be a pretty big number that they would allow you to load this, you know, say plus 5%. You know, what I generally do is draw this kind of a box, and then when I figure my weight in CG, if it falls within that box, I'm okay. You know, I can go test. Okay, we'll not run out of time here. Too many war stories. Now, we'll pass that on. This too. Why not work? Here is, well, this is for a Piper Saratoga, but Cherokee 6 looks similar. Well, you got a ballast type, and we have 75 pounds of lead shot that we can put in the nose baggage compartment to help move the CG. And we'll probably use that. Well, yeah, this talks about how to collect the data. I just give you some examples here of things that you should have on your cards, you know, the date, type, airplane. And I think the last thing I have on there is who was involved. Here's what will happen. If you're doing a test and you're working, you know, and there's several of you, several flight test engineers and pilots working the program, what will happen is, you know, you go out and you get this data and the data piles up, and you come back and you got a question. You can't remember. If you know who was on the test program with you, you can go, hey, do you remember such and such? So it's a good idea to put down who was involved in the test. These are just some tolerances that the FAA allows. Again, probably not worth. Except this one shouldn't be used to circumvent the regulation. you can see that on a Cherokee 6 with plus or minus 7%, here's the FCG. These things could almost overlap. So if you wanted to measure stall speed and you got it back here, you could kind of cheat. Okay, you could almost be doing it at an FCG, which means you have more control authority and you're going to get a lower stall speed. So they say don't do that. All right, we'll be looking at all of these kinds of data collection methods during the course. And here's how we go about doing the corrections. Correct for instrument error. You know, the instruments each have an error, and I'll try to remember to bring an instrument in for you all to take a look at that I've got cut away. Position error. I'm going to be talking more about this. I won't spend a lot of time on it, but the airplane flying through the air has its own error. And we call it position error. It depends on where you put the static source. We'll talk more about that. Then we correct for non-standard conditions down to a standard day at sea level. And then we can make a presentation. We engineers like standard day sea level data. We can do something with that. Pilots don't understand that, okay, for the most part. So we have to expand it back to what I call standard, non-standard conditions, you know, specified, I should probably say it's specified non-standard conditions for the pilot's handbook. Okay, well, this is the last one. The atmosphere, you've seen this when you're probably in high school at least. Some things, standard atmosphere, we deal with a standard atmosphere, and generally at flight test we adhere to the 1962 standard atmosphere. If you go to the library, you can probably find standard atmospheres as recent as maybe last year. What you'll find if you look and compare them, they'll only change in about the 4th decimal point. So it probably isn't worth the effort to update, you know. So some flight tests we've kind of stuck to this one, at least the FAA has. All right, questions? It's lunchtime. We'll see you in 1:15. How's that?